So this is response C for linear algebra. So the material that I have given you in the Google Drive previously is in Bahasa Indonesia, and I didn't have time to convert it to English. So I think it should be okay. But don't worry, some parts are in English because I took it directly from the textbook. Okay. So we'll just start. The first one is about the eigenvectors and diagonalization. So this chapter is pretty straightforward because you only study this one, the eigenvector. This is the main part of the chapter. Okay, so this is the first part, which is the definition of an eigenvector. So basically, if I have an operator like this, mana tuh pen? So basically, if I have an operator like this, or rather an operation where A is a transformation matrix, if we multiply A to X, let's say we get a matrix like this, a straight line. This transformation is also equivalent to when X is multiplied by a scalar known as lambda. And this lambda is known as the eigenvalue. And the X here is said to be the eigenvector corresponding to lambda. Yeah. And transformation rules also apply here. Can I scribble here? Bisa coret-coret. Anyways, nggak bisa. Or this one I cannot scribble, so yeah. Coba. Bisa. Okay. So AX is like a transformation. Yeah. And then this transformation is equivalent to when this very same X is multiplied by a constant. So yeah. This is what the basic concept of eigenvector. Okay. Sebentar. Prince only temporary. Jadi ini nggak dicoret-coret. Okay, so this is the basic steps to calculate the eigenvalue and the eigenvector. So basically, the first step here is to calculate this lambda I minus A, where I is your identity matrix. The next step is to find the value of lambda, or the eigenvalue, based on the characteristic polynomial that you get from step 1. Step 3, let's say you already get the values of lambda. You might get 2 or 3 values or more, possibly, depend on the matrix. You plug this value into this equation, and then you solve for the value, you solve for X. Then you get a solution with infinite number of solutions. So basically, you will get something with a parameter t that you should solve, which is the end result. And then after we get the coefficient of the parameter, that you will get multiple coefficients because of the multiple number of lambda. And because of that, the coefficients formed will be the basis for what we call as the eigenvector, the basis of the eigenspace. Later, I will show you in the question how to solve it. Okay, so this is just an additional information. So if we have a triangular matrix, whether it's upper triangular, lower triangular, or diagonal, the eigenvalues of A are the entries on the main diagonal of A. So you don't have to perform these general steps. All you have to do is just take the main diagonal. Okay. Next, this one. This one sometimes appear in exams because last time I did the exam, this topic appeared, which is about algebraic multiplicity and geometric multiplicity. So basically, for algebraic multiplicity, you just look at each value of lambda and how many times they appear in the question. Okay, later I'll show you. For geometric multiplicity, it is the solution to this, and I mean the dimension to the solution of this, or to put it simple, how many parameters are there for each value of lambda. Okay, so this is for diagonalization. For diagonalization, we are trying to convert this matrix A to become a diagonal matrix D using a matrix P that has an inverse. Because P has an inverse, therefore, the determinant of P cannot be 0. And the basis of P, and P consists of the basis of the eigenspace of matrix A. So you have to perform the procedures to get the eigenvectors, then you're going to get P. And the basis for this eigenspace must be linearly independent to each other. But that won't matter because they'll just ask you to diagonalize the question. Okay, so first step that you do is you find the eigenspace of A, and then you turn it into matrix P. Then you find the inverse of matrix P, and then you find the diagonal matrix using this formula. Okay. Okay, so now I go to the question. Okay, so this is the question. Where first we're going to find the basis for the eigenspace and the algebraic and geometric multiplicity. Okay, so what we do first is, so the first thing I do is lambda I minus A equals to lambda minus 2, 0, 2, 0, lambda minus 3, 0, 0, 0, lambda minus 3. Next, I find the determinant of lambda I minus A equals to 0. So for the determinant, we're going to take the cofactor expansion on the first row. This is the general procedure. We just do first row. So this is lambda minus 2, lambda minus 3, lambda minus 3, 0, 0, 0. There's 0 here, so we ignore this. There's 2 plus 2 multiplied by 0, 0, 0, lambda minus 3. And so this is, if you calculate, this is already automatically 0, so we ignore that. So we're going to get lambda minus 2, then lambda minus 3 squared equals to 0. Okay, so this is what we call your polynomial, characteristic polynomial. And then we plug in the value. Your lambda is 2 and 3. So the first thing that we do is plug in the value of lambda equals 2 into this equation. If we plug in 2, we're going to get 0, 0, 2, 0, negative 1, 0, 0, 0, negative 1. The next step is to perform what we call the elementary row operations to solve lambda I minus a x equals to 0. So in order to solve this, the easiest thing we can do now is to multiply the second and third row by minus 1. So this is 2 minus 1 are 3 minus 1. So this is 0, 0, 2, 0, 1, 0, 0, 0, 1. Okay, so for this, next thing to do is to knock out the first row. So it's R1 minus 2 R3. We're going to get 0, 0, 0, 0, 1, 0, 0, 0, 1. And as you can see, the one that has leading ones are this one and this one. The first row doesn't have leading one. So therefore, x3 equals to 0, x2 equals to 0, and x1 equals to a parameter t. And so x1, x2, x3 is equivalent to 1, 0, 0, t. So this is your first one. Okay, now we can find the algebraic and geometric multiplicity. So for algebraic is the number of times lambda appears as a solution. So here for 2, lambda only appears once, so your algebraic multiplicity is 1. For geometric, since there's only one, the dimension of the solution space is only one, only this one. Therefore, your geometric is also 1. Now for lambda equals to 3. For lambda equals to 3, the matrix that you're going to get is 1, 0, 2, 0, 0, 0, 0, 0, 0. And so you don't have to do anything because you already get the reduced row echelon form. Now we just have to apply parameters. So x3 equals to t, x2 equals to s. Only this one has leading one, first row. So therefore x1 is negative 2x3, which is negative 2t. And so this is, we can write it like this, equals something times t plus something times s. So x1 is negative 2t, so this is negative 2. x2 does not have t, so this is 0. x3 has t, so it's 1. For x2, for s, only x2 has s, so we put 1 in the middle and 0 and at the top and bottom. And for this case, your algebraic, since 3 occurs 2 times, or there's a square here, which means it occurs 2 times, so your algebraic is 2. And for geometric, there are two, the dimension is 2 because there's 2 coefficients here, so the geometric is 2. Oh yeah, and bear in mind, the pattern will not always be like this. There are some cases where your algebraic multiplicity is not the same as your geometric multiplicity. So please bear that in mind. Okay, so the basis for the eigenspace, therefore, will be 1, 0, 0, comma, negative 2, 0, 1, comma, 0, 1, 0. So this is your basis for your eigenspace of A. Okay, so the next part of the problem is to do the diagonalization process. So as usual, we already found matrix P, which is the basis of the eigenspace of A. So we'll write here P equals to 1, 0, 0, negative 2, 0, 1. Okay. And 0, 1, 0. The next thing we have to do is find the inverse of P, and we can just do it like this. 1 minus 2, 0, 0, 0, 1, 0, 1, 0. And at this side is the identity matrix. like this. The easiest thing we can do now is to switch the second and third row. Like this. The next thing that we do is to calculate the initial, to knock out this, the -2. So what we do is R1 plus 2 R2. So this is what we're going to get. And over on this side, it's 0, 2, 0, 0, 1, 0, 1, 0. And so this is your identity matrix. This is your P inverse. But in this case, this is P. This is I inverse. Sorry, this is I, not I inverse. So now we have P inverse equals 1, 0, 0, 0, 0, 1, 2, 1, 0. So now we have, so the next part is to find the diagonalization diagonal matrix. Sorry, just D equals P inverse A P. So all I have to do is just write it down. Let's do 0, 0, 0, 3, 0. And -2, 0, 0. Is it -2, 0, 3? Okay. The next thing to do is to write P. Okay, so now we do the multiplication, and you're going to get kali seperti biasa, you're going to get 204,003,030 times 1 minus 20,001,010. And if you continue further, you're going to get 200,030,003. This is your diagonal matrix. And if you take a look at the eigenvalues that we obtained, we can see that it's the same as the diagonal matrix here. Just do 3, 3. 3 occurs twice because it appears twice in the polynomial solution, the characteristic polynomial. Okay, so this is how, so let's say when you're doing your exam and then you miscalculate the value of D multiple times, or there's something wrong with P or P inverse, just give this answer directly and you're not going to be wrong. Okay, so the next thing we do is to find A to the power of 1000. So for this, since D equals P inverse AP, in order to get the expression of A, we multiply P on the left side of D. And bear in mind, P inverse equals P inverse P equals I. Okay, and I times A equals to, sorry, equals to equals to A. Yeah. B, C, yeah. And we're going to get I, A, P. Then we're going to times P inverse to the left, sorry, to the right of D. So this is equals to I, A, I. So this is P, D, P inverse equals to A. So for A is 1000, P, D 1000, P inverse. This is the formula. and P inverse, they're not multiplied, but they're not raised to the power of 1000. Yeah, so it's just the D. So this, we can just write 102, 001, 010 times 2 to the power of 1000, 3 to the power of 1000, 3 to the power of 1000 times P inverse 102, 001, 010. And if you continue on, you're going to get the answer. But to make it quick and simple, I'm not going to solve this. So if you want to do it, go do it at your own time. Okay. So next, we're going to move on to the next chapter, which is inner product spaces and orthogonality. So for definition, generally speaking, your inner product space is the dot product of two vectors. However, the hasil kali dalam or inner product space is actually a generalized version of your dot product. And because of this, we get this expression. And we have also this relationship that will be of use later. The first one would just symmetry, which is u comma v equals to v comma u. And if there's addition or subtraction, it will be like this. And if one of them is multiplied by a scalar, this is the solution. Here. Oh yeah, this is the norm, which is the length of the vector. Oh yeah, in the previous one I gave you, there's something wrong with the equation. I already fixed it, so this is the solution. This is the norm of a vector v. This is the difference between the two vectors, which is this. And I recommend using this and this for all cases because this is the a very powerful formula. Okay. Yeah. So this is, as I said before, an important one. So we have something like this. So if we have 0 multiply in an inner product space between a vector, the result will always be 0. And this is the plus minus property I mentioned just now. And for this one, where we have a scalar, if we have ku comma fv, the result will be k times f, the scalar, times u comma v. So this is the general formula for step E. And for this one, we don't have to study that. And now we have something called weighted inner product space. So basically, this is a special type of product space where you have weighting, which is W1, W2, and W3, up to Wn. You might, in your exam, you might get a question that looks like this. And all you have to do to solve it is something like this. It's actually simple. Yeah. Just treat it as if you're treating a regular inner product space. And you're good to go. Okay, ini sudah. Oh yeah. This inner product space, this weighted inner product space, can be also expressed as a matrix like this, where this is the relation. You can use this, or you can use the easiest form, which is this. And for the matrix A, this A is a diagonal matrix in which in the diagonals, it contains the square root of the weighting, the weights. Okay. And actually, as I said before, since this inner product space U comma V is a general process, so therefore it can apply to M and N. or square matrices or polynomials like this, and in rare cases, integrals. However, in the exam, I doubt you will get something like this. But if it actually comes out, yeah, then I suggest you be careful. Okay. And next here is to find angle. For Cauchy-Schwarz, you don't have to pay attention too much to this. The most important one is the angle here, this one. And this theta here, bear in mind, must be in between 0 and pi, or in between 0 and 180 degrees. Okay. Yeah, for now we can go to the question, which is on inner product space. So we'll do it step by step. For this one, for 2v minus w, comma 3u plus 2w, how do we solve this? The first thing that we do here is to treat this part as a constant. So we have 2v, comma 3u plus 2w minus, because there's negative here, w, comma 3u plus 2w. And then we can continually expand this to get 2v, comma 3u plus 2v, comma 2w minus w, comma 3u minus w, comma 2w. Ini we can use, I'll just put it side to side. So we can use this one. Mana tuh? This one. Yeah, this one. And so we can pull out the constant. So 2 times 3 is 6. So 6 is v, comma u plus 2 times 2, 4, v, comma w minus 3 w, comma u minus 2 w, comma w. However, note that this w, comma w is the norm of w squared. Okay. So keep this in mind. And for this one, b, if you get a distance like this, the easiest thing to do is to solve it as a square. What do I mean by that? You get this and then you square it first. And you're going to get u plus v, comma u plus v. And this expansion is equal to the norm of u squared plus 2 times u, comma v plus the norm of v squared. And so all you have to do to get u plus v is just square root the entire thing up there. Okay. Now we're done with this one. Now we move on to the bottom one, which is to find the norm of u and v. And now we're going to go back to the slide, which is in this part. Get the norm of u and v, which is this. We just take the cells inside the matrix and then square them and then add them all. Should be straightforward. So this square root 1 squared plus 2 squared plus negative 3 squared plus 5 squared. This is equal to square root 1 4 plus 9. Sorry, 5, 30, 39. So we do the same thing for V, just square root 16 plus 36 plus 64. And this is square root 116. Okay. Next, we have to find this for U comma V, because in order to find the distance between U and V, we need this. So U comma V is the corresponding cells multiplied by each other and then added to each other. So we have here 1 times 4 is 4. 2 times 6 is 12, so plus 12. Minus 3 times 0 is 0. 5 times 8 is 40. So we get 40. And so the solution is 56. Now we have to find D U V. And D U comma V squared, as usual, use the square, is U minus V comma U minus V. And from this, the solution is similar to the top, however, there's a negative there. So this is U squared minus 2 U comma V plus V squared. So this is 39 plus 116 minus 2 times 56. If you calculate, you're going to get 43. And so D U comma V equal to root 43. And next we have to find the angle. Now for the angle, we use this formula. So the angle is cos theta equals to U comma V comma length norm of U times norm of V. So this is equal to 56 over root 39 times root 116. However, because in your exam, I think you're not allowed to use calculator. So I'm not sure something as difficult as this will come out of the exam. So we'll just leave this here so you can calculate the theta if you want by using cos inverse on this. Okay, so next is orthogonality. So I think this is mentioned in chapter 3, where if we have the dot product of two vectors that is equal to 0, it means they are orthogonal or perpendicular to each other, which means the angle is 90 degrees between them. This is the general form. And if you want, you can prove the Pythagoras theorem using vector forms. This is, if you want to prove it, go ahead. By bearing this in mind. And next we have, I will introduce you to two type of sets, which is an orthogonal set and an orthonormal set. A set is called orthogonal if the inner product of each of the components in the set is equal to 0. And for an orthonormal set is an orthogonal set where each of the vectors has norm equals to 1 or a length of 1. Okay. So here we have coordinate vectors. In order to save time, I'll just skip to the main point, which is the Gram-Schmidt process. And this Gram-Schmidt process is a bit of a tricky process where we convert a basis into an from a regular basis to an orthonormal basis. And so the Gram-Schmidt process consists of two different components, which is the Gram process and the Schmidt process. And here we see that the Gram process changes on orthogonal basis, changes a regular basis, sorry, to an orthogonal basis. So this is the formula. And a Schmidt process converts an orthogonal basis to an orthonormal basis, which is the continuation of the gram process. Okay. And the next is QR decomposition. This is QR decomposition, where we decompose A into two different matrices, which is matrix Q and matrix R. So the first thing that we do is, let's say we have a matrix A. What we should do is we should perform Gram-Schmidt process on the column vectors of A. So we take the columns and then we perform Gram-Schmidt process on them. After we perform Gram-Schmidt, we're going to get a matrix Q. And from this matrix and from the result of the Gram-Schmidt, we can also obtain a matrix R, which is an upper triangular matrix, which looks like this. Okay. Now we're going to go into inner product space, so which is this one. So now the first thing that we should do here is to perform the Gram-Schmidt process. So first we define the vector u. 1 is 1, 0, 1. The vector u2 equals to 0, 1, 2. The vector u3 is equivalent to 2, 1, 0. And then the first thing we do is to perform the Gram process. So for the Gram process, u1 is equivalent to v1 and v2 is equivalent to u2 minus u2 comma v1 divided by the length of v1 times v1. And u2 comma v1 is 2. The length of v1 is square root of 2 if you calculate it. So we just plug in those values, 0, 1, 2 minus wait. Oh, there's a square there. So squared. So it's 2 over 2 times 101. So the base is 0. Sorry, equals 0. The basis. So the result is negative 1, 1, and 1. Now we're going to do for V3. So V3 is U3 minus U3 comma V1 over V1 squared V1 minus U3 comma V2 over length of V2 squared times V2, which is equal to 210 minus U3 comma V1 is 2 times 1, 0, 0. It's also 2. Length of V2 is root 3. So we're going to get 2 over 2 minus 101 minus U3 V2 U3 comma V2 is minus 2 1, so it's minus 1, so here's plus 1 over square of V2 is 3, so this is 210. Sorry, not 210, but negative 1, 1, and 1. So the solution to this is 2 minus 1 is this is 1, 1, 0, minus 1. Plus 1 over 3 minus 1, 1, 1. So the top solution is 2 over 3. Middle solution is 4 over 3. The last solution is negative 2 over 3. And so this is the result of your gram process. Next, we move on to the Schmidt process. I might have to add a page. And so now we have the Schmidt process. So we get Q1, which is 1 over V1 times V1, which is since the length of V1 here is root 2, so we have 1 over root 2 times 101 V2 is the same thing. The solution times V2, which is 1 over root 3 times negative 111, comma, V3 equals, what is the length of V3? The length of V3, 1 over 3 times 4 plus 16 plus 4, which is root 24 over 3. And this is the same as 2 root 6 over 3. So we flip that upside down. So this is 3 over 2 root 6 times 2 over 3, 4 over 3, and negative 2 over 3. So this is your orthonormal basis. And from this, we can get the matrix Q, which is this one, Q1, which is 1 over root 2, 0, 1 over root 2, V2, which is negative 1 over root 3, 1 over root 3, and 1 over root 3. And final result is V3, which is 1 over root 6, 2 over root 6, minus 1 over root 6. So that's your Q. And for your R, it is U1, comma Q1. This is QR. So it's U2, comma Q1, and comma Q1. So this is U1, comma Q2, U1, comma Q3. It. So we have 0, 0, 0. This is U2, comma Q2. This is U2, comma Q3. In the end, we have U3, comma Q3. For now, U1, comma Q1 is this. It's 2 over root 2. Is equivalent to root 2. U1 over Q1 is equal to U1 comma Q2, sorry, is equal to Sorry, this is supposed to be Q2, 1, U3, Q1. Sorry. This is U1, 2, 3. This is U3, Q2. This is U3, Q2. Is it correct? Yeah. So U2, Q1 is also over equals to, and U3 comma Q1 is equal to also equivalent to. If you want to calculate it at your own, go ahead. Next is U2 comma Q2. It is equivalent to 3 over root 3. It's equivalent to root 3. And U3 comma Q2 is it's negative 1. Wait. Plus 1 over root 3 equals to negative root 3 over 3. And finally, we calculate U3 comma Q3, which is equivalent to 210 8 over 3 times 3 over 2 root 6, just cross, 4 over root 6. So this is the values for the matrix. You just have to plug all these values into this matrix, and you're going to get the R matrix. And then you can try A equals to QR, and if it is correct, that means your calculation is correct. If they're not equal, if they're not equal, which means there's something wrong with your calculation. So okay, for now I'll leave it here in order to save time. Next, we move on to orthogonal matrices and then the diagonalization process. Okay. So basically, a matrix is considered orthogonal if it has this property. Let's say we have matrix A, and if we transpose matrix A, and then if we find the inverse of matrix A, we're going to see that the transpose matrix and the inverse are the same. So this is what we call orthogonal matrix. Hence, because of this relationship, we can say that A times A transpose is equal to A transpose times A, which is equal to the identity matrix. If you want, this is not that important. You can read it if you want. And so this is orthogonal diagonalization. So this is important. The only difference between the one in eigenvectors is that what is P? If we look at the one in eigenvectors, which is here, the P is the basis of the eigenspace of the matrix A. However, in orthogonal diagonalization, the P here, the matrix P, is the basis of the eigenvector that has undergone Gram-Schmidt process. And then the rest is the same. However, the P, we don't find the inverse of P, but rather we just use the transpose. Okay. So for this one, just for this simplicity, I took an example from the textbook where first you find, in this part, you find the eigenvalues and the eigenvectors, which is U1, U2, and U3. And then you perform Gram-Schmidt process on these three. And after that, you will get the matrix P. And then finally, you just transpose this matrix P, and then you're going to get the diagonalization. And you see the result is the same as the eigenvalues, which is 2 and 8. And 2 appears twice here. So which is why there's 2 values of 2 here. Okay. Now we move on to the linear transformation. Okay, so for the linear transformation, the first part is basic transformation, where you have 6 types of transformation. The first one is dilation and contraction in X and Y direction. So basically, dilation and contraction is just expansion in the direction of one of the axes. So if it's expansion in X direction, that means only X changes, Y doesn't change. And the opposite goes for the Y direction. However, I have to ask for forgiveness here because I cannot help you much in this chapter. In this part, because in this part, it's memorization of the matrices. However, you can somehow logically understand the process. So let's say if it's expansion or compression in the X direction, that means only X changes, but Y doesn't change. If Y doesn't change, that means the value is 1, the matrix here. And also remember that if K is larger than 1, it is expansion, meaning it gets bigger. However, if it's between 0 and 1, that means that it is a compression, meaning it gets shorter in the respective direction. So same goes here. And next one is rotation. For rotation, this is the matrix. If theta is positive, meaning it goes counterclockwise like this. However, if it's negative, it goes clockwise. Why? Because if it's negative, look at the direction it's going. It's going to the negative quadrant. So if this is positive, that means it's going to negative. If it's positive, it's going to positive direction. Okay, and bear in mind it's cos theta and sin theta here. However, bear in mind that the angle they give, that the problem might give you, might be angles with predetermined with simple values like 0, 30, 45, 60, or 180. So that I believe you already memorized when you were studying for CMAC or in high school or something like that. Okay, same principle applies for 3D. How do you memorize this? the negative is on the top right, and it's always sin. And the pattern is always like this. It doesn't change. It's always cos, cos, cross to the diagonal is cos. The other direction is sin. Doesn't change. Same goes here. So you just have to analyze that if it's positive x-axis, if x is the rotation of axis, that means it doesn't change. If same goes for y and z. This y is a bit different, so just be careful here. And for z, this is the matrix. As usual, I cannot help you much. This is memorization. So this is reflection. So if reflection in x-axis, meaning you just imagine that y changes, so x doesn't change. So for about y-axis, x changes, y doesn't change. For reflection to y equals to x, we can identify two properties here. So this is, we have line y equals x, and we have line y comma x to x comma y, or the line between the object and the mirror image. The line between the object and mirror image is perpendicular to the y equals x. So that's a property that you have to that you can remember. And the distance between the perpendicular distance, between x and y comma x. The perpendicular distance between x comma y and the line here, and the line y equals x, which is the reflection line, is perpendicular. It's the same as this. So this is D, this is D. So it's the same. Jaraknya antara x, y dan garis cermin itu sama aja dengan jarak antara y, x dan garis cermin. Okay. So yeah. This is 3D reflection. However, for 3D, because since this one is it's based on the line x-axis, y-axis, y equals x, you might get y equals mx or mx plus c, but that's a rare case. You might get this as well. 3D. However, for 3D, it's no longer reflection on a line. It's based on a plane, which is xy plane, xz plane, and yz plane. The easiest way to memorize it is, if let's say xy plane, what is not present here? Z is not present here. So therefore, your Z is negative. That's how I memorized it. XZ plane, Y is not present, so negative Y. Corresponding matrix apply. YZ plane, X is not present, X is negative. Okay. So this is orthogonal projection. So basically for orthogonal projection, one of them becomes 0, the other one becomes 0. Y-axis onto x-axis, X doesn't change. Onto y-axis, Y doesn't change. So that's how I memorize for this one. So if you have your own way of memorizing, go ahead. Now this is expansion and contraction. This is similar to example 1a and 1b. However, if you look at the matrix here, for expansion and contraction, the value of k is, it happens in all x's. If previously it happens only in x direction or y direction, now it happens in all direction. Okay, so this is, and the same rules of k applies. If it's larger than 1, it's getting bigger. If it's smaller than 1 but greater than 0, meaning it's shrinking, getting smaller. And next, we have shear. Shear is like if the object is getting blown by the wind. You can read this on your own and understand how it happens, because this question rarely appears, but just be prepared. So for shear, we call y, I think if I remember correctly, y is what we call the invariant lines, because y doesn't change in this case for x direction. But you can go on Google and check just in case I'm wrong. So this is shear. okay, in y direction, sorry, in x direction and y direction. Okay, next we have something called transformation composition. Well, let's say we have TA, which is a transformation from M to K, and TB is a transformation from K to M. So it's like jumping. Like, let's say, I think I have a picture here. I don't think it's here, but anyway, I think it's in chapter 4. This one. So basically, if we have transformation, this one, where TA is from Rn to Rk, and Tb is from Rk to Rm. Therefore, the composition of TB-TA, like this, TB-TAx, is you jumping from this plane to this plane, from Rn to Rm. So basically, there's no stopover. There's just a jump. You go to you take the direct route to Rm from Rn. And let's say we have transformation like this. We can express it in the form of a matrix. Let's say TBX is B and DAX is A. And so we can express it as a matrix like this. The same goes with the N transformation. That means it's whatever times B times A. However, bear in mind order matters, okay, in terms of transformation, and especially when you're dealing with matrices, your what do you call? Your transformation matters. About your order matters. Because if your order is different, then you're going to get a different outcome, which is different from what it is intended. And it's also worth noting that T2 to 0 T1 is not always the same as T1 to T2. However, there are some cases where they are the same, like we have the composition of two different rotations. You can take a look at the book, example 2, chapter 4, 10, and a composition of two reflections towards x-axis followed by y-axis, which is shown in example 3, chapter 4, 10. Okay, if you want to have a look at the book, go ahead, but I won't show you, but just to save time. And oh yeah, if you have a trouble understanding this concept, just imagine in high school, back in high school, when you're studying fungsi komposisi or function composition, where you have FGX or GFX or GOFX, FOGX. Yeah, this is basically the concept is this one. The next one is one-to-one transformation. So basically, for one-to-one transformation, one transformation only has one solution. If one transformation has more than two, one transformation has one solution. If two transformations give the same solution, like this one, two transformations, they give the same solution, they're not one-to-one. What do I mean is, let's say this is TAX. If I transform TAX, let's say this is point A and point B. If I transform point A to Rm, there's one unique value. If I transform point B, there's one unique value. That is one-to-one. However, if I transform A and it results at the same point as I transform B, it's not one-to-one. Gitu. Example is rotation is not one-to-one, and orthogonal projection is not one-to-one. Okay, so this is kernel and range. We have an example, I think, down there. Yeah. kernel and range. So this is TA. So for the kernel is the null space of A, or all the vectors in Rn that experience mapping to zero plane. And the range is all vectors in Rm that is a result of TA with at least from at least one vector in Rn. That's the best. This one is not important. To put it simply, the kernel of a transformation is the null space of A, and the range is the column space of A. I think we've learned null space, column space in chapter 4. Okay, so ini for Rn to Rn is that A must be invertible, TA must be 1-to-1. Oh yeah, this is important. For TA to have an inverse, it must be 1-to-1. Okay, just like here. Has to be 1-to-1, and automatically the determinant must not be equal to 0. Okay. Next is proving. So basically, this is the same concept of inverse. That if we change the order of the composition between A and its inverse, we're going to get the same result. So it doesn't matter. To put it simply, inverse transformation is the reverse of a transformation. An example here. So let's say we have a rotation of 45 degrees clockwise followed by an expansion of 5 times. If we reverse the inverse of this is a compression 5 times followed by a rotation 45 degrees counterclockwise. And guys, make sure you pay attention to this, because not only the operation reverses, but the order also reverses. So this is inverse and this is 1-to-1. And another type of transformation that we should know is called onto transformation. So basically, I'll just be quick here. Let's say we have matrix A. Now, matrix A has 2 rows. Okay. And so if we see here, is it onto? Yes, because A has a pivot in every row. Now, if you look at this one is not onto because it does not have a pivot in every row. Okay, this is the official language, but then, however, even I have difficulty understanding what this means, to be honest. So just use the example just to make sure you understand. Okay. Now that's just what we've gone through. Now we go here. Oh yeah, guys, make sure you understand onto and 1-to-1, yeah, because it applies in a concept known as isomorphism later. And so these are the axioms for a linear transformation. So for a transformation to be linear, it has to fulfill these 3 operations, especially this and this. Or depending on the question, because usually the question gives you which axiom that you need to prove. Okay. And so these are types of transformation. From here, we have the general transformation. We have the zero transformation, where if we transform U, it will lead to 0. We have identity transformation. We have contraction or dilation. We have projection. We have change in basis, and we have inner product space. So these are just some transformation. Now we go to question 5, which is the proving. So now here we know that there's a linear transformation like this. Next, we are asked to determine whether it follows this and this. So now here we're going to say that U, let's say, is U1, U2. and V is V1, V2. Okay, so let me write the transformation. Okay, so now we're going to prove axiom 1, which is T U plus V equals TU plus TV. Jadi TU plus V. First we identify TU, which is T U1 U2. So this is U1 minus U2. This is U1 and U2. For TV, the concept is the same, which is T V1 V2 equals V1 minus V2 V1 V2. And for T U plus V, it is transformation of U1 plus V1, U2 plus V2, and U3 plus V3. This is equal to sorry, kok ada U3? Sorry. So this is equivalent to U1 plus V1 minus U2 plus V2. And this is U1 plus V1, this is U2 plus V2. Now if we expand this, we can get U1 minus U2, U1, U2 plus V1 minus V2, V1, V2. So this is equivalent to TU, as you notice, plus TV. And so axiom 1 is obeyed. Now we go to axiom 2, which is T KU equals to KTU. Okay. Okay, so KU is KU1, KU2. Hence TKU equals KU1 minus KU2. This is KU1 and KU2. Now, as you can see, we can factorize the K out like this. And so it's equivalent to K times TU. And so axiom 2 is obeyed. Therefore, T is linear. Okay, now we go back here. And as mentioned before, we have kernel and range. Now we go here, kernel and range. Let's say we have a transformation like this. So the first thing that we should do is to convert the outcome, the outcome into matrix form. Like this. Then we solve for this, where the for a zero transformation. Like so. And then this is the process where we do the row operation. And we get this. This is the final result. And because of this, there's only one, the dimension is only one, right? So therefore, your null T is only one. And we just use the relationship rank T plus null T equals n, where n is the number of columns. We can say, and because there are 3 columns, so 3 minus 1 is 2. So therefore, your rank is 2. Like this and this. You can also use another way, which is the column vector. We express the column vector. And we look at here. And we see that column 1 and column 2 has leading 1. Therefore, these two are the bases. And because of this, there are two. The dimension of the column space is 2. Therefore, your rank is 2. Okay, continue. Now, this is an important question as well, where we have, I think, question 6. Now, question 6 is similar to this. However, in this one, the transformation is known. And for this one, the transformation is not known. So basically, the first thing that you do, okay, itu nanti. Now now for this one, if you have a question like this, where the transformation is not known, but you are given a basis like this, and the basis experience transformation, the first thing that you do is express the basis as a linear combination of x1, x2, and x3. Like this. And then we solve it. We solve for C1, C2, and C3. Now we know here that C1 equals to, in this case, we know that C1 equals to x3, and C2 equals to x2 minus x3, and C3 equals x1 minus x2. So we plug this result into here. So this is what we're going to get. This is the transformation. This is the general form, sorry. And next, all we have to do is just input the transformation, and this is the final result that we're going to get. Hence, we can compute this t2 minus 3,5 here using this formula. There's another way to do this that I can show you, but not now. Okay, I might include it with, I might put it in the drive. Okay, so if you are confused with this step. Now here, isomorphism. Isomorphism basically is a transformation that is both onto and one-to-one. Now here we have natural isomorphism, which means that the isomorphism, ya udah seperti itu, is already like this to begin with, so which is why it's natural. Okay, so next. Now, how do we prove that a transformation matrix is an isomorphism? The first thing that we do is prove whether it is linear. And from here, we've seen that it's linear already because it obeys both axioms. Then we prove that whether that it is one-to-one and it is onto. However, before all that, we need to show that A is invertible, and indeed here we see that A is invertible. Next, we prove that A is one-to-one by solving for this. That A is one-to-one by solving for AX equals to 0. And from the row operations, we can see that A has a unique solution for zero transformation, which means that it is one-to-one. Next one, to prove that it is onto, we give general solution A, B, and C. And we can see from the solving that A is onto because all three has leading one. And since we've proven here that A is one-to-one and onto, we can say that A is an isomorphism. Okay. Now this is where it gets confusing, which is general transformation that involves changes of basis. So usually questions will ask you to find this one, the matrix A, this one. So let's say you have this X, it's a cycle, basically. Now if you want to understand this, go ahead, but I'll just tell you the gist of it, the general procedure. So let's say you have an old basis You have an old basis. You input the old basis into the given transformation. And then you express the old basis using as an expression of a new basis. So like this. This is the new basis. V1, V2, V3 is the new basis. U1, U2, and U3 and so on is the old one. Okay. Then we find the value of A, B, C, D, E, F, etc. Then if we have the value of A, B, C, D, E, F, we can combine it to get a solution of this TU BXN. Now this is the example shown. Okay. So the first thing we do is we have this transformation. Then we have U1 and U2. All we have to do is just input U1 and U2 into the transformation, and we get the results. Next, we express the results of U1 and U2 as a linear combination of the new basis, which is V1, V2, and V3, like this. Okay, so next we solve for V1, V2, and V3, and for your information here, we don't have to solve it one by one. To save time, we can solve both A and B simultaneously. And now we have this. This is the final result of A1, A2, and A3. And as you can see, for 1, 2, and 3. And as you can see here, the change is the Gauss-Jordan operation is not complete. So, but however, if you were to observe, this is for 3, this is for 2, this is for 1. The values have been obtained here in the white. So therefore, we have this. This is your transformation. 1, 0, minus 2, and 3, 1, minus 1. So this is what you get. Okay, so this is for similarities. So let's say we have two matrices, they are the same. Wait, so I'll try here. Okay, we have a bit more. So yeah, any similarities? So basically, A and B, they are related with the matrix P. Such that, so yeah. This is a property of similar matrices. So they have the same determinant, A equals to B. They are both invertible. They have the same rank and nullity. They have the same eigenvalue, and they have the same dimension of eigenspace. And so they are related by this equation. Unfortunately, I cannot show you about similarity. However, I can show you in another question. So I can show you in another document that I will upload. So make sure you check the G drive given simultaneously. Okay. It's not simultaneously, regularly. Okay. So now we're done with that. Now, kok ditutup? Sorry. Now we move to the question. Now here we have question 6, where we have this transformation. The first thing that we do is input the old basis here. So T, I think I don't write here. So we have T 101, T 010, and T and T 2 minus 1, 1. Transformation is 2x3, x1 plus 2x2 minus x3, and minus x1 plus 3x3. That's the transformation. So I already calculated in advance, so I just need to write down the values in order to save time. Okay. So if we plug in the old basis, we're going to get this. So next, we're going to do the symbol equating 202 equals to A 200 plus B 131 plus C minus 211. So next 020 equals to D 200 plus E 131 plus F minus 211, and then 2 minus 11 equals to G 200 plus E, or G, okay, H 131 plus I minus 211. Okay, so now this is done. So now we have to solve for A, B, C, D, F, and G, H, I. The process is quite long, so I won't discuss it too much here. So if you want to find it on your own, go ahead. I'll just write down the final results. You're going to get but don't worry, I'll give the solutions later, the clearer ones in the drive that has been given to you previously. This is 3.5, this is -1, 2. So this is the final solution. And for TW, for B, you're going to get 4.5, 13 minus 1.51 minus 1, 3.5 minus 1, 2, times -100. And here you're going to get -4.51 minus 3. This is your result. Okay, so next, linear transformation. I'll be quick. So note the transformation P1. So what is P1? P1 is A plus BX to form R2. Okay, so find T1 minus 2x. So P0 equals 1 minus 2 times 0 equals 1. P1 equals 1 minus 2 times 1 equals -1. So T1 minus 2x equals to 1 comma minus 1. This is A. For B, show that T is a linear transformation. So T Px equals to A plus B, which is equal to 1, 0, 1, 1, A, B. How do I get A and A plus B? This. Plug in x equals to 0, and you're going to get it. And x equals to 1, you're going to get this. Next, we're going to do the reduced row operation on the matrix. So like this. To do is R2 minus R1. We're going to get, hence, we've shown that it's linear. Show that, sorry, this is C. It's 1 to 1, sorry. Show that T is a linear transformation using the axioms. Let's say P1x is A1 plus B1x, and P2x is A2 plus B2x. Therefore, T P1x is A1, A1 plus B1. T P2x equals to A2, A1 plus B1. And P1x plus P2x is A1 plus A2 plus B1 plus B2 x. And so the transformation is A1 plus A2, A1 plus A2 plus B1 plus B2. And so if you separate it, T is equal to T P1x plus T P2x. Now, if you want, you can also go and prove the second theorem. So, yeah. T KPX equals to T KA plus KBX equals to KA plus KB equals to KA plus B. Hence, this is KTPX. Hence, we've proven that it's linear. Now for D, T inverse, we have Tx equals to P0, Px, sorry, P1, right? Ini biar bagus. Therefore, the inverse, T inverse, is actually P0, T inverse P0, P1 equals to Px. So in other words, this is equivalent to A, this is equivalent to A plus B. So we're asked the inverse 2, 3, right? 2, 3, yeah. So A equals to 2, A plus B equals to 3, therefore B equals to 1. Therefore, your Px is equivalent to 2 plus x. That's your D. If you want to graph it, this is 2. There, it's a straight line. So this, let's say this is 1, this is 3, this is 2, this is 4, and so on. Okay, so now 8, we prove whether it is an isomorphism or not. So for proof it is linear, that's easy. So TU is U1 minus U2, 2U3, U2 minus U1. Oh, beta. So this is times U1, U2, U3. TV is V1 minus V2, 2V3, and V2 minus V1. And TU plus V is U1, yeah, U1 plus V1 minus U2 minus V2. This is 2 times V2 plus U2 sorry, U3 plus V3. And this is U2 plus V2 plus U1 plus V1. And if you separate it, you're going to get TU plus TV. And now I'm going to prove TKU. I'm sorry if I'm going fast because I want to finish quickly so that you can rest for tomorrow's test. So if you have any exams tomorrow. So this is K. KU1 minus KU2. This is KU3 and KU2 plus KU1. Factorize the K. Get U1 minus U2, U3, U2 minus U1. So this is K, T, U. So we have proven it is linear. Now what I'm going to do now is kill two birds with one stone and prove 2 and 3 at the same time. How? Just by doing this. So now we move R2 and R3. Get 1 minus 1, 0, minus 1, 1, 0, and 0, 0, 2. And so now what we do is R1 plus R2. We're going to get 0, 0, 0, negative 1, 1, 0, 0, 0, 2. And because of this, I don't need to continue further. Because of this, it means it has infinite solution. Because of this, T is not 1-to-1. T is not onto. Therefore, T is not an isomorphism. So we're done for the night. Thank you for coming. Later, I'll give this material in the G drive. Yeah, so I'm sorry if it took a long time or if there are any parts that are unclear. So thank you. And don't forget to fill in the absence. Yeah, the absency. Let me stop share. So thank you for coming. Thank you for listening. Okay, so good night.